Before anything existed, before light, before space, before time itself, there was no silence, because silence needs time to pass. And there was no darkness, because darkness needs space to exist. There was, quite literally, nothing. Not an empty room. Not a black void. Nothing at all. And yet, from that complete absence, everything you have ever known somehow appeared. The stars above you, the ground beneath you, the breath you are taking right now, all of it traces back to a single beginning. For most of human history, this idea felt impossible. Ancient civilizations imagined God shaping the cosmos by hand. Philosophers argued that the universe must have always existed. Even modern scientists once believed the universe was eternal and unchanging. Then, less than 100 years ago, we discovered something unsettling. The universe is expanding. Every galaxy is moving away from every other galaxy, as if space itself is slowly stretching. And if we gently rewind that expansion, step by step, patiently and carefully, everything leads back to one moment, unimaginably hot. Dense beginning, where space, time, and matter were all compressed together. This is what we call the Big Bang, though the name is misleading, because it wasn't an explosion in space. It was the birth of space itself. There was no center, no edge, no outside, just the universe coming into existence everywhere at once. This video is not about rushing to conclusions or drowning in equations. It is about slowing down enough to understand how scientists uncovered this story, what the Big Bang truly means, and why it matters that you exist in a universe with a beginning. Over the next 2 hours, we will move carefully, almost gently, through the earliest moments of reality, watching the universe grow, cool, and organize itself until stars ignite. Galaxies form, and eventually, consciousness emerges to ask the very question we are exploring now. So take a breath, let go of the noise of the world for a while, and imagine the impossible, that everything you know came from almost nothing, and that by understanding the beginning of the universe, we are also learning something profound about ourselves. In the very first fraction of a second after the beginning, the universe existed in a state that defies normal language. It was not small in the way an object is small, because there was no surrounding space to be small within. Instead, all of space itself was compressed into an unimaginably hot and dense condition. Physicists call the earliest meaningful instant the Planck time, a moment so brief that our current laws of physics struggle to describe it. During this period, the forces we now recognize, gravity, electromagnetism, and the nuclear forces, were not yet distinct. Reality was unified, intense and simple in structure, but extreme in energy. Almost immediately, something extraordinary happened. Space began to expand at a staggering rate in a process known as cosmic inflation. This was not matter flying outward through space, but space itself stretching everywhere at once, faster than the speed of light, which does not violate relativity because nothing was moving through space. Space was growing. In a tiny fraction of a second, the universe expanded from far smaller than an atom to something larger than a galaxy. This sudden expansion smoothed out irregularities, explaining why the universe appears remarkably uniform in every direction. Yet it also magnified tiny quantum fluctuations, microscopic variations in energy, planting the seeds for all future structure. When inflation ended, the universe was still incredibly hot, but it began to cool as it expanded. Energy started transforming into particles, following Einstein's equation that energy and matter are interchangeable. Quarks, electrons, and other fundamental particles emerged from the cooling energy soup, appearing and annihilating each other in rapid cycles. As the universe continued to cool, quarks combined to form protons and neutrons, the building blocks of atomic nuclei. This period was chaotic, yet governed by precise physical laws as matter slowly gained stability. Within minutes, protons and neutrons fused together to create the nuclei of the lightest elements, hydrogen, helium, and traces of lithium. This process, known as primordial nucleosynthesis, set the chemical foundation of the cosmos. For a brief time, the universe was like a blazing furnace where nuclear reactions occurred everywhere at once. But as expansion continued, temperatures dropped too low for fusion to persist. What remained was a vast, expanding universe filled with hot plasma, a glowing fog of charged particles and radiation. Light could not yet travel freely because electrons scattered photons constantly, keeping the universe opaque, like a dense luminous cloud. Time marched forward, not in dramatic explosions, but in steady cooling and gradual change as the universe patiently prepared the conditions for complexity. Hundreds of thousands of years passed in this state, an unimaginably long time compared to the violent first seconds, yet essential for what would come next. Eventually, the universe cooled enough for electrons to bind with nuclei, forming the first neutral atoms. In that moment, light was finally able to move freely through space. The universe became transparent, and the photons released then have been traveling ever since, stretching and cooling with the expansion of space. Today we detect this ancient light as the cosmic microwave background, a faint afterglow that fills the entire universe and serves as a direct snapshot of the cosmos when it was only about 380,000 years old. This light is not just evidence of the Big Bang. It is a reminder that the universe has a memory and that we are capable of reading it. After the universe became transparent, it entered a long, quiet era often called the Cosmic Dark Ages. There were no stars, no galaxies, and no planets, only vast clouds of hydrogen and helium drifting through expanding space. Gravity, however, was already at work. Tiny differences in density, amplified from the earliest moments of inflation, slowly grew stronger as regions with slightly more matter pulled in their surroundings. Over millions of years, these denser areas collapsed inward, heating up under their own gravity. When temperatures and pressures became high enough, nuclear fusion ignited, and the first stars were born. These stars were unlike most stars we see today. They were massive, short-lived, and intensely bright, composed almost entirely of hydrogen and helium. In their cores, simple elements were fused into heavier ones, creating carbon, oxygen, and other elements essential for complexity. When these early stars exhausted their fuel, many ended their lives in powerful supernova explosions, scattering newly formed elements into space. This stellar recycling enriched the surrounding gas, allowing later generations of stars to form with more diverse chemistry. Over time, stars gathered into galaxies, held together by gravity and shaped by the invisible influence of dark matter, a mysterious substance that does not emit light but outweighs ordinary matter by a significant margin. Galaxies collided, merged, and evolved, forming the large-scale structure of the universe we observe today: filaments, clusters, and vast cosmic voids. Billions of years after the Big Bang, in one unremarkable region of one spiral galaxy, a star formed with a disk of leftover material orbiting around it. Within that disk, particles collided, stuck together, and gradually built planets. On at least one of those planets, conditions allowed chemistry to become complex, molecules to replicate, and life to emerge. Over immense stretches of time, life evolved, adapted, and eventually became capable of reflection. Humans are not separate from this story. We are a continuation of it. Every atom in your body was forged either in the first minutes after the Big Bang or in the heart of a long-dead star. The calcium in your bones, the iron in your blood, and the carbon in your cells are ancient, shaped by cosmic processes billions of years before Earth existed. Understanding the Big Bang is not merely about tracing the universe backward. It is about recognizing that the universe's history is written within us. And yet, despite how much we have learned, profound mysteries remain. We do not know what caused inflation, what dark matter truly is, or whether the Big Bang was the absolute beginning or part of a larger cosmic cycle. The universe continues to expand, possibly accelerating due to dark energy, hinting at a future that may be cold, vast, and quiet. Still, from a beginning of extreme simplicity, the universe developed complexity, structure, and awareness. In telling this story slowly, we are reminded that existence did not rush to create us. It unfolded patiently, governed by elegant laws, allowing enough time for stars to shine, worlds to form, and minds to awaken and ask how it all began. As the universe continued to age beyond its first few billion years, it did not simply drift towards stillness. Instead, it grew more intricate, more dynamic, and in some ways, more mysterious. Galaxies matured, their shapes influenced by rotation, collisions, and the invisible scaffolding of dark matter. Spiral galaxies, like our own Milky Way, formed graceful arms where gas clouds compressed and gave birth to new generations of stars. While elliptical galaxies grew large and smooth after repeated mergers, inside galaxies, stars lived out predictable yet dramatic life cycles. Smaller stars burned slowly and steadily for billions of years, while massive stars lived fast and died young, ending in supernova explosions that briefly outshone entire galaxies. These explosions were not acts of destruction alone. They were acts of creation, forging the heaviest elements, gold, uranium, and many others, and scattering them into interstellar space. Over time, clouds of enriched gas collapsed again, forming new stars surrounded by disks of dust and debris. Within these disks, matter assembled piece by piece into planets, moons, asteroids, and comets. Planetary systems became common outcomes of star formation rather than rare accidents. Some planets ended up too hot, others too cold, but a small fraction existed in regions where liquid water could persist, opening the door to chemistry of astonishing complexity. On at least one such world, Earth, simple molecules began interacting in ways that allowed them to store information and reproduce. Life emerged not as a sudden miracle, but as a gradual consequence of physical and chemical laws playing out over immense spans of time. From single-celled organisms to multicellular life, from simple nervous systems to brains capable of memory and imagination, evolution shaped living beings in constant dialogue with their environment. Eventually, a species arose that could look up at the night sky and wonder where everything came from. This moment when the universe became conscious of itself is not separate from cosmic history, but deeply rooted in it. The atoms that make up human brains were assembled in ancient stars. The energy that fuels our thoughts originates from nuclear fusion in the sun, which itself is a descendant of earlier stellar generations. When we study the cosmos, we are not outsiders peering in. We are participants examining our own origin story. Yet even as life flourished and intelligence emerged, the universe itself continued to evolve on scales far beyond human lifetimes. Galaxies kept drifting apart as space expanded, and this expansion began to accelerate, driven by a mysterious force we call dark energy. Unlike gravity, which pulls matter together, dark energy appears to push space apart. It's becoming more dominant as the universe grows larger and emptier. Its nature remains unknown, but its effects are measurable and profound, shaping the ultimate fate of the cosmos. Looking outward, astronomers see galaxies moving away faster the farther they are, a pattern that confirms the universe's expansion and ties directly back to the Big Bang. Looking inward, physicists attempt to reconcile general relativity, which describes gravity and large-scale structure, with quantum mechanics, which governs the smallest scales of reality. The earliest moments of the universe lie at the intersection of these two theories, a realm we do not yet fully understand. Questions linger. What exactly triggered inflation? Was the Big Bang truly the beginning of time, or merely a transition from an earlier state? Could there be other universes, each with its own laws of physics, forming a vast multiverse? These ideas remain speculative, but they arise naturally from attempts to understand the evidence we observe. Science, at its core, is not a collection of final answers, but a method of refining questions, guided by observation, experimentation, and humility before the unknown. As we project our understanding forward in time, the future of the universe appears both majestic and sobering. If dark energy continues to dominate, galaxies beyond our local group will eventually slip beyond our observable horizon. Their light stretched and faded until they disappear entirely. The night sky, once rich with distant galaxies, will grow darker for future observers, making the universe seem smaller and lonelier than it truly is. stars will continue to form for billions of years. But the raw material for star formation, cold gas, will slowly be used up or dispersed. Eventually, star birth will decline, leaving behind long-lived dim stars, stellar remnants, in vast stretches of darkness. On even longer timescales, trillions of years into the future, stars like the Sun will exhaust their fuel and fade into white dwarfs, neutron stars, or black holes. Galaxies will become collections of stellar corpses orbiting quietly in expanding space. If current theories hold, black holes themselves may slowly evaporate through a process known as Hawking radiation, returning their mass to the universe as faint energy over unimaginable durations. What remains at the end could be a cold, dilute cosmos approaching thermodynamic equilibrium, a state sometimes called heat death. Yet even this bleak-sounding future is not devoid of meaning. It is the natural continuation of the same physical laws that allowed complexity to arise in the first place, from a hot, dense beginning to a vast, cooling expanse. The universe follows a coherent narrative shaped by expansion, gravity, and time. Understanding this arc gives context to our brief moment within it. Human existence occupies a tiny slice of cosmic history, but it is a slice rich with awareness, creativity, and curiosity. We live at a time when the universe is old enough for stars to have created heavy elements and stable enough for life to flourish, yet young enough that distant galaxies are still visible and the echoes of the Big Bang are still detectable. This makes our era cosmically special, not because humans are central, but because the conditions for understanding exist right now. When we listen to the faint hum of the cosmic microwave background, we are hearing the afterglow of creation itself. When we study galaxies billions of light years away, we are looking back in time, witnessing earlier chapters of the same story that led to us. The Big Bang, explained slowly, is not merely a tale of explosions, particles, and equations. It is a story of emergence, patience, and continuity. It reminds us that complexity can arise from simplicity, that order can grow from chaos, and that the universe does not need intention to produce meaning. Meaning emerges because beings like us can reflect, connect, and care. In the end, the Big Bang is not just about how the universe began, but about how it became capable of asking questions. And as long as there are minds to wonder, the story of the universe remains unfinished, continuing not only through stars and galaxies, but through thought itself. Even after tracing the universe from its earliest moments through the rise of stars, galaxies, and life, there remains a deeper layer to the Big Bang story that is less about what we see and more about how we know. Our understanding of the universe's beginning is not built on belief or imagination alone, but on a careful accumulation of evidence, measurements, and reasoning that stretches across generations of scientific inquiry. One of the most powerful pillars of this understanding is the expansion of the universe itself. When astronomers observe distant galaxies, they find that their light is shifted toward the red end of the spectrum, a phenomenon known as redshift. This shift increases with distance, revealing that galaxies are moving away from us and from one another. This pattern is not random. It follows a precise relationship that points to an expanding fabric of space. By mathematically reversing this expansion, scientists arrive at a universe that was once far denser and hotter than it is today. This is not a philosophical argument, but a measurable one, grounded in observation. Another critical piece of evidence comes from the cosmic microwave background, the faint afterglow of the early universe that fills all of space. Its uniform temperature with tiny fluctuations measured to extraordinary precision matches predictions made decades before it was even detected. These slight variations in temperature are not imperfections. They are the fingerprints of the universe's earliest structure, encoding information about the density, composition, and geometry of the cosmos. From these measurements, scientists can determine the age of the universe, its rate of expansion, and the relative amounts of ordinary matter, and dark energy. The remarkable consistency between independent lines of evidence gives the Big Bang theory its strength. It is not a single idea resting on one observation, but a framework supported by many. Yet, this framework also reveals its own limits. As we push closer to the very beginning, our theories begin to falter. General relativity, which describes gravity and the large-scale behavior of space and time, works exquisitely well for stars, galaxies, and the expansion of the universe, but it breaks down when applied to the extreme conditions of the earliest moments. Quantum mechanics, which governs the behavior of particles at the smallest scales, excels in describing the microworld, but does not yet mesh seamlessly with gravity. The Big Bang sits at the boundary of these two theories, highlighting a gap in our understanding rather than a final answer. This is why scientists speak carefully about what happened at time zero, acknowledging that our current models describe the universe from fractions of a second onward, not necessarily the absolute beginning. Some hypotheses suggest that the Big Bang was not the creation of everything from nothing, but a transition from a previous state of bounce from an earlier contracting universe, or the emergence of our universe from a larger multiverse. These ideas remain speculative, not because they are unscientific, but because they lack direct observational evidence. Science advances not by declaring certainty, but by testing ideas against reality and discarding those that fail. This willingness to live with uncertainty is not a weakness. It is one of science's greatest strengths. It keeps the story of the universe open-ended, inviting deeper questions rather than closing them off. On a human level, the implications of the Big Bang extend beyond cosmology into philosophy and perspective. Knowing that the universe had a beginning challenges intuitive notions of permanence and forces us to confront the fleeting nature of all structures, from galaxies to civilizations. At the same time, it reveals a profound continuity between the cosmos and ourselves. The laws that governed the universe's birth are the same laws that govern the atoms in our bodies today. There is no sharp boundary between cosmic history and human history. One flows into the other seamlessly. When we look at the night sky, we are not just observing distant objects. We are witnessing different epochs of our own origin. The light from faraway galaxies has traveled for billions of years to reach our eyes, carrying with it information about the universe when it was much younger. In this sense, astronomy is a form of time travel, allowing us to reconstruct a story that spans nearly 14 billion years. This long view has the power to reshape how we think about meaning and significance. In a universe so vast and old, human life might seem insignificant at first glance. Yet significance does not arise from size or duration alone. It arises from awareness, from the ability to understand and reflect. The universe, through us, has developed the capacity to study its own beginnings, to measure its age, and to ponder its fate. This is not a claim of human superiority, but a recognition of an extraordinary fact. Complex systems governed by simple laws can give rise to consciousness. The Big Bang, explained slowly, reveals that the universe did not rush toward complexity, nor did it aim for any predetermined outcome. It unfolded step by step, allowing order to emerge naturally from fundamental interactions. That this process led eventually to beings capable of curiosity and compassion is not guaranteed, but it is real. As we continue to refine our instruments and theories, new discoveries will undoubtedly reshape parts of this story. We may find evidence of physics beyond our current models, uncover clues about the nature of dark matter and dark energy, or learn that the universe's beginning is more subtle than we imagined. Each discovery will not erase the Big Bang, but deepen our understanding of it, adding nuance and context. In this way, the story of the universe mirrors the story of knowledge itself, always expanding, never complete. To explain the Big Bang slowly is to resist the urge for simple answers and to embrace the patience required to truly understand. It is an invitation to sit with the immensity of time, to appreciate the delicate balance of forces that shaped everything we know, and to recognize our place within that vast continuum. The universe began in a state of extraordinary simplicity, and over billions of years it evolved into something capable of wonder. That fact alone suggests that understanding the cosmos is not separate from understanding ourselves. We are not merely observers of the universe's story. We are chapters within it, still being written, still asking how it all began and what it means to exist in a universe that had a beginning at all? As we arrive at the end of this long and careful journey, it is worth pausing not to rush toward a conclusion, but to sit quietly with everything that has unfolded. The story of the Big Bang is not a loud ending or a dramatic final revelation. It is a gentle widening of perspective. We began with a universe so hot, so dense, and so simple that it barely resembles the reality we know today. And yet, through the steady unfolding of physical laws, that simplicity grew into unimaginable complexity. There was no guiding hand shaping galaxies one by one, no blueprint for stars, planets, or life. There was only expansion, cooling, gravity, and time. And still, from those ingredients, everything emerged. This realization can feel unsettling at first, because it removes the comfort of a universe built specifically for us. But in its place, it offers something deeper, a sense of belonging to a story far larger than any single life, culture, or era. The atoms in your body are ancient travelers. They were present in the early universe as simple particles, later forged into heavier elements in the hearts of stars, scattered across space by stellar explosions, and eventually gathered into a planet capable of supporting life. Nothing about you is separate from the cosmos. You are not in the universe. You are of it. When you understand this, the boundary between the personal and the cosmic begins to dissolve. Your existence is not an interruption in the universe's story, but a continuation of it, shaped by the same forces that shaped galaxies and stars. The Big Bang also reminds us of the power of patience. The universe did not become what it is overnight. It took hundreds of thousands of years for atoms to form, hundreds of millions of years for the first stars to ignite, and billions of years for planets and life to arise. Complexity was not forced. It was allowed to emerge gradually. In a world that often demands instant results and quick answers, the universe offers a different lesson, that meaningful structures take time. Even understanding the universe required centuries of careful observation, debate, error, and correction. The Big Bang was not accepted easily or immediately. It challenged deeply held assumptions about eternity and stability, forcing scientists to rethink the nature of space and time themselves. That willingness to question, to admit uncertainty, and to follow evidence wherever it leads is one of humanity's greatest achievements. It shows that knowledge is not a fixed destination, but an ongoing process, one that mirrors the universe's own expansion. Every answer leads to new questions, and every discovery opens new frontiers of mystery. Rather than diminishing the story, these uncertainties enrich it, reminding us that reality is deeper than our current understanding and that there is always more to learn. There is also a quiet humility embedded in the Big Bang story. It tells us that the universe does not revolve around us, that we occupy no special central position in space or time. We live on a small planet orbiting an ordinary star in one galaxy among hundreds of billions. And yet within this vastness, something remarkable has occurred. The universe has produced beings capable of curiosity, empathy, and reflection. Significance, then, is not granted by size or importance on a cosmic map, but by awareness and connection. The fact that we can reconstruct the history of the universe from faint radiation and distant starlight speaks to the extraordinary capacity of the human mind. Through science, the universe has found a way to observe itself, to trace its own origins, and to wonder about its future. This does not elevate us above the cosmos. It ties us more deeply to it. Our thoughts, questions, and emotions are expressions of the same natural processes that drive stars to shine and galaxies to form. In understanding the Big Bang, we are not standing apart from nature. We are participating in it at a reflective level, looking forward. The universe will continue its journey long after our individual lives and even our civilizations have passed. Stars will be born and die, galaxies will drift apart. The cosmos will slowly change in ways that may one day make it unrecognizable. The universe does not promise permanence, but it does offer continuity. Everything transforms, nothing truly disappears. Even in the far future, when the universe grows colder and darker, it will still be shaped by the same laws that governed its fiery beginning. This perspective can reshape how we think about our own lives. Our time is brief, but it is not meaningless. We exist during a rare window when the universe is rich with structure and light, when the echoes of its beginning are still detectable, and when conscious beings can ask questions about existence itself. That alone makes this moment extraordinary. To live in such a universe is not just to exist, but to witness. Every time you look at the night sky, you're seeing light that has traveled across billions of years, connecting you directly to the past. In that sense, the universe is always speaking. And understanding the Big Bang is one way of learning how to listen. As this story comes to a close, it does not ask you to hold on to specific facts or numbers, though those are important. It asks you to hold on to a feeling, a sense of awe balanced with humility, wonder tempered by patience. The Big Bang is not a cold or distant idea. It is the reason there is anything to feel awe about at all. It is the reason there are stars to admire, questions to ask, and minds capable of understanding. When explained slowly, the Big Bang becomes less about a moment in the distant past and more about an ongoing process, a universe still unfolding, still expanding, still becoming. We are part of that becoming. Our curiosity, our creativity, and our search for meaning are not accidents. They are natural outcomes of a universe governed by consistent laws and vast amounts of time. In recognizing this, we find a quiet reassurance that existence does not need to be rushed to be meaningful. And that understanding often comes not from speed, but from stillness and attention. So as the final moments of this journey settle, imagine the universe not as something that began and ended in a single explosive event, but as a long, continuous story that stretches from the first fraction of a second to this very moment and beyond. A story in which stars are born, elements are forged, life emerges, and consciousness reflects on its own origins. The Big Bang is the opening line of that story, not its conclusion. And as long as there are minds to wonder and voices to tell the tale, the universe's story continues, carried forward through understanding, curiosity, and the simple act of looking up and asking where it all began. The Big Bang Theory, at its core, is humanity's most carefully constructed explanation for how the universe began and evolved, not as a sudden guess, but as a conclusion drawn from decades of observation, reasoning, and evidence. It tells us that the universe was once in a state of extreme heat and density, and has been expanding and cooling ever since. This idea did not emerge fully formed. It grew slowly as scientists noticed patterns in the sky that could not be ignored. When distant galaxies were observed, their light appeared stretched, shifted toward red wavelengths, revealing that space itself is expanding. This expansion implied a past when everything was closer together, leading naturally to the idea of a beginning. The Big Bang Theory does not claim to explain why the universe exists or what caused it to begin, but it does remarkably explain how the universe changed from a simple, hot state into the complex cosmos we observe today. It accounts for the abundance of light elements like hydrogen and helium, which formed in the universe's first minutes. And it predicts the existence of the cosmic microwave background, a faint glow left over from the time when the universe first became transparent. The discovery of this ancient radiation was one of the strongest confirmations of the theory, turning the Big Bang from a bold hypothesis into a well-supported scientific model. Yet the theory remains open to refinement. It does not describe the very first instant with complete certainty, because our current understanding of physics cannot fully unite gravity and quantum mechanics under such extreme conditions. This limitation is not a failure, but a sign that the Big Bang Theory is part of a larger, evolving quest to understand reality. It has already transformed how we see our place in the universe, showing that space and time themselves have a history and are not eternal backdrops. Perhaps most profoundly, the Big Bang Theory connects the largest scales of the cosmos to the smallest details of our existence. It explains how the universe created the conditions necessary for stars, galaxies, planets, and eventually life to arise. Every scientific measurement, from the motion of galaxies to the temperature of ancient radiation, adds another thread to this vast narrative. When considered slowly and thoughtfully, the Big Bang Theory becomes more than a scientific explanation. It becomes a framework for understanding change, impermanence, and emergence. It reminds us that the universe is dynamic, that it has grown and evolved, and that we are part of that evolution. Far from reducing existence to cold mechanics, the theory reveals a universe capable of generating beauty, complexity, and awareness through simple, consistent laws acting over immense spans of time. In this sense, the Big Bang Theory does not diminish wonder, it deepens it, offering a story where everything, including us, shares a common cosmic origin.